Hi and welcome back. So we're going to be looking at our next topic in higher level energetics, which is entropy, which will lead on to a couple more equations that we need to look at. So let's get started with a few definitions. When we're talking about entropy, what we're talking about is the tendency towards something becoming disordered. So if we think about a solid, it being highly ordered is a lower probability than a disordered liquid, which is the higher probability. One way to think about this is if you were to stand with a pile of bricks and throw them, it's improbable for the bricks to fall in a highly ordered arrangement. What's more likely is for them to fall in a random assortment rather than ordered. So this would have a higher level of disorder. So what we're saying is that spontaneous processes tend towards a higher level of disorder. This is a universal law, and you may have heard the term entropic death. And entropy itself is a tendency for the system or the universe to head towards a greater level of disorder. So spontaneous changes are ones that occur without the addition of energy other than that required to overcome the initial energy barrier, i.e. activation energy. Okay, so a spontaneous process occurs without the addition of energy other than that to require the overcome the initial energy barrier. We've seen this in redox processes where we have spontaneous redox processes which allow us to create galvanic cells. Diffusion of a gas is also an example of this natural tendency to increase their mixing or disorder. Dissolving, evaporation, melting, these are all spontaneous changes. Most of these changes tend to be exothermic, however a couple are endothermic, these being things like our evaporation, dissolving and melting. These phase changes are actually all endothermic as we go from a lower ordered arrangement in the physical state to a higher energy level of disorder. So one way to think about it is a spontaneous process is something that will occur without the addition of energy. So it's like a ball rolling down a hill. Once you get it started, you give it a push, it will continue to do so without an extra energy being put in. Whereas a non-spontaneous process is like trying to push something up a hill where we need to continue to apply the energy in order for that process to occur. So spontaneous changes, we've seen examples of these that naturally occur are things like water evaporating, solids dissolving, or gases moving together. These are examples of spontaneous processes, but you can also see that they also increase the level of disorder. Okay, so here where water was a liquid and into a gas, we're increasing disorder. Where solids dissolve into the solute into the solvent, we have a higher kinetic energy and a greater level of disorder. Same goes with the mixing that we see between gases. So mathematically and scientifically, we refer to this level of disorder as entropy. This quantifies the degree of disorder of a system, and it refers to the distribution of available energy among particles. So the more ways energy can be distributed, the higher the entropy. Ordered states have small energy distribution. They have a small number of solutions that give rise to that ordered state, so they have low entropy. Disordered states have larger energy distributions and they are considered to have a high entropy. So high entropy equates to a higher level of disorder. As time moves forward, it has been stated that matter and energy become more disordered and the total entropy of the universe will increase. And this is what we mean towards the universe tends towards greater entropy. So if we look at this, entropy is given the symbol capital S, and it is used to describe the randomness or disorder of a system. So being able to define the system again, as we did with exothermic and endothermic reactions, is critical when talking about entropy. The second law of thermodynamics states that the entropy of an isolated system, when not in equilibrium, will tend to increase over time. So an increase in disorder produces a positive delta S or change in entropy. Okay, so an isolated system will tend, when not in equilibrium, because remember equilibrium will have the forward and reverse reactions occurring at the same time, so when not in equilibrium will tend towards disorder. So we can look at a number of examples where we have increasing entropy. Dissolution of a salt, such as that of ammonium nitrate, paying attention that this is one of the unusual endothermic processes that we see. This is highly endothermic. The ammonium nitrate is highly ordered lattice arrangement, and when it dissolves, the ions spread throughout the solution in a random arrangement. So we see an increase in entropy. And that increase in entropy, that dissolution process, is an endothermic process. We can also see this in other changes of state. These are endothermic examples of entropy again. In all of these cases, the arrangement of particles becomes more disordered. So we see water going from a solid to liquid, or a liquid to a gas, iodine subliming from a solid to a gas. Because these are going from a low energy state to a higher energy state, we do see them being endothermic processes, but the entropy increases. Okay, so we see here that vaporization, positive enthalpy, positive entropy, condensation, negative enthalpy, negative entropy. For a decomposition reaction, again, this is an endothermic process, the decomposition of calcium carbonate. Ammonium carbonate. 1 mole of ammonium carbonate produces 4 moles of gases. So we're going from a highly ordered lattice arrangement into a highly disordered system where we see 4 moles of gas being evolved. Of course, if we increase temperature, the increased temperature results in an increase in entropy, even if there is no state change. So we see an entropic change, an increase in entropy, when we have the kinetic energy of the particles increasing as they gain more freedom to move. That more freedom to move means that we have a higher entropy. So all substances have a greater entropy at room temperature than they do at 0 Kelvin, i.e. they have a greater freedom of movement, therefore a higher level of disorder. What this means mathematically is that we need to be able to predict an entropy change. So when we go to do this, we need to note the states of the reactants and the products. If a state change is occurring from a solid to a liquid, or a liquid to a gas, or a solid to a gas, then entropy must have increased. We are increasing the level of disorder. The relative number of mole of reactants and products. If there is a greater number of mole of particles on the product side, then entropy has generally increased. If we go from 1 mole of reactants to 4 mole of products, then we have a higher entropy. So if you think of each of the following reactions, I want you to pause the video and see if you can work out which would have the most positive delta S. This means an increasing entropy value. Okay, so a positive delta S means that the entropy would have increased. So if you have a look at this one, we have number A, we have letter A here. We have methane gas plus oxygen gas in a combustion reaction going to CO2 and H2O. Our second example is CO2 plus hydrogen forming methanol and H2O. The synthesis reaction where we have aluminium and sulfur producing aluminium sulfide, the ionic compound, and then methane plus water to give H2 and CO2. So I want you to have a look at each of these, think about what we've talked about, and then see if you can predict, then come back to see the answers. Okay, hopefully you had a look at this box over here, which is informing us that we need to refer to the changes in state and the number of moles. Okay, so the change in number of moles of gas is often a key factor. If we have a look at A, it's gaseous all the way, and we have 3 reactant mole particles on the left-hand side and 3 on the right-hand side. This would mean that delta S, the change in delta S, is going to be close to 0 because everything's in the gaseous state, and of course we aren't changing the number of mole of reactant or product particles, so we're not seeing a great increase in disorder. Okay, so let's have a look at each of these and the way that they're written. So in this reaction, there are 3 mole of gaseous reactants and 3 mole of gaseous products. Delta S would be almost, if not equal to 0. For B, we can see that we have 4 moles of gaseous reactants going to 2 moles of gaseous products. In this case, delta S, we have gone from more to less, so delta S must be negative. We have decreased the level of disorder in this system. Here we can see we have no gaseous products or reactants to look at, but we do have 5 moles of solid going into 1 mole of an ionic solid. So because we have more reactant particles going to less reactant particles, okay, again, the entropy of the system will have decreased. We have increased the order, so therefore delta S will be negative. And in our last example, we can see that methane with water going to 3H2 and CO2, we have 2 mole of gaseous reactants going to 4 mole of gaseous products. We have increased the number of moles, so we have increased the disorder. Delta S is going to be positive. The entropy of this system has increased. So this is a table actually from your textbook, which summarizes the entropy changes for melting, boiling, condensation, sublimation, deposition, freezing, precipitation. This is a good idea to have in your notes as an example of situations where delta S is going to be positive or negative, okay, just to give you an idea of a bunch of examples. Okay, so this video is going to go for a little while because I want to do the maths of this as well. So settle in and come along for the ride. So we've talked about what entropy is in terms of the system. Now we're going to define standard entropy, remembering that the naught raised as a superscript lets us know that it is under standard conditions. And this means that we're going to be using the standard conditions thermodynamic table, which is table 12 in our data booklet. So entropy with this symbol is measured under standard conditions. So the absolute entropy of a substance at 298 Kelvin and 1.01 times 10 to the 2 kilopascals, or 101 kilopascals. The units of entropy are joules per Kelvin. Okay, remembering that a lot of times we're going to be dealing with gases, so we want to have our temperature in Kelvin. The entropy change is calculated in the same manner as enthalpy change for a reaction using the values given in the data tables. So, standard entropies of elements and compounds are all positive, okay, unlike standard enthalpies of formation, which are 0. So the standard enthalpies of elements and compounds are positive. For a reaction, A plus B goes to C plus D, we can determine the change in entropy for the reaction by summing the entropy of the products and minusing the entropy of the reactants. So delta S naught is products minus reactants, and we're going to get the values for delta S for each of the things in our equation from table 12. Okay, so this is an older table. You can see here that the entropy is given in joules per Kelvin per mole. This is our standard enthalpy. And here we can see that ammonia as a gas is 193. Be sure to check your states, because remember, these are standard states, what state they would be in 298 Kelvin. Okay, if it is in a state different to this, then the value would be different. Okay, so what I want you to do is, again, pause this video, calculate the standard entropy change for the following at 25 degrees C. So you're going to use table 12. You're going to sum each of the entropy values for the reactants and sum each of the entropy values for the products. And then you're going to do products minus reactants. So have a go at each of these 3 equations and come back and see if you got them right. Okay, here's the solutions for each of these, remembering that these are based off an older table, so some of these values may vary from the ones that you got from your data booklet. But what we're going to do is take our products, the entropy of carbon dioxide, plus 2 times the entropy of water, and we're going to minus the entropy of methane minus 2 times the entropy of oxygen. So remembering that these values are per mole, so if we have more than 1 mole in the equation, the coefficient is more than 1, we need to multiply that value by the molar coefficient. When you do this, you should end up with 592 minus 596 joules per Kelvin, and it's going to have a negative entropy value. So we can see that it's a very small, okay, but it's very close to 0, as we predicted in the earlier questions. In B, when we go through, we're going to have the entropy of methanol plus the entropy of water minus the enthalpy of carbon dioxide and 3 times the entropy of hydrogen. This means that we will end up with a negative 180 joules per Kelvin, which shows a large decrease in entropy for this reaction, which is as predicted because we went from 4 moles of gas to 2 moles of gas. That is a significant drop in the disorder of the system. Lastly, for C, where we had 2 mole going to 4 mole and we predicted a positive entropy change, using our products minus reactants, we have 3 lots of hydrogen plus CO2 minus CH4 and H2O, which gives us a positive entropy change of 232 joules per Kelvin. Again, when we're doing these, we need to make sure we include the sign. Okay, so we're not going to assume positive. Whenever it is positive, we need to indicate the positive nature of this because it's telling us the direction. Okay, so that's calculating basic entropy. I'll do the next one where we start to talk about entropy of the surroundings and a few other things that we need to make note of in a subsequent video because this one's long enough as it is. Have a go at those, practice the examples in your textbook and see how you go. Hopefully these ones should be quite straightforward to understand. And I'll see you in class.